Let's take a look at some of the different types of media that we might be using to interconnect network components. For example, if we're interconnecting a couple of Ethernet switches, we might use unshielded twisted pair. Or we're connecting out to a client machine, that might use unshielded twisted pair. What if we're interconnecting a couple of buildings on a campus? We've got a switch in each building and the distance is greater than 100 meters. Maybe we're going to be using fiber optic cabling. Or if we're maintaining an older Ethernet network like 10 base 2, 10 base 5, we might even see coaxial cabling.
One media type that we used to see a lot more of than we do today is coaxial cabling. Coaxial cabling was popular back in the early to mid 90s and late 80s when it was used in 10 base 2 and 10 base 5 Ethernet networks. We don't see it much anymore, but back in those days, you would have a coaxial cable that would weave its way through your office space, from one desk to another desk, from one office to another office, and in workstations like a PC would tap in to this coaxial cable. You see on screen what's called a T connector, and we would take our PC and connect into that T connector, and the specific kind of connector being used here is called a BNC connector, and different literature defines BNC differently. Some literature will say that BNC refers to a British naval connector, while other literature says that BNC stands for Bayonet Neil Consulman. But however you want to define it, with this connector, you would take the cable, the coaxial cable running from a PC, and you would push and twist it into this connector to lock it in. And this coaxial cable might look similar to what you use in your home for your cable TV. However, it's different. It's a different kind of coaxial cable. What you use in your home for cable TV is probably either RG59 or RG6. RG6 being the newer and better standard, but those cables have an impedance of 75 ohms. The coaxial cable used in networks has an impedance of only 50 ohms. And the specific type of cable that was used for 10 base 2, that's the thinner version, sometimes called ThinNet, was RG58. It had an impedance of 50 ohms. The thicker cable used by 10 base 5, also referred to as ThickNet, it was a cable that was similar to RG8, but it had some extra shielding. A metallic braid went around the outside of the cable, gave you a little bit of extra protection from electromagnetic interference. Again, coaxial cabling, very popular back in the days of 10 base 2 and 10 base 5. We really don't see it much these days for network use, unless you want to consider the fact that many people get broadband access through their cable television company using a cable modem. From that perspective, I guess you could argue that we still are using coaxial cable in modern day networks. The network media that we're most likely to work with as we're maintaining a local area network is twisted pair cabling. And let's think about what it means to have twisted pair cabling. As you notice on screen, we have a pair of wires that are twisted together. And the twists are there to protect the wiring from electromagnetic interference, or EMI. And you'll notice that the different pairs of wires have a different number of twists per inch. Again, this is done for electrical characteristics. We're trying to prevent electromagnetic waves from being picked up by this wiring. And also, we don't want these wires to become antennas and start radiating. If we start transmitting data at a high rate through twisted pair cabling, if the twists are not tight enough, we become an antenna and we could start interfering with other devices. We don't want that. And when you hear about twisted pair, often you hear the term UTP for unshielded twisted pair, but there is another type, and that's shielded twisted pair. Let's contrast those two. Very popular back in the token ring days, shielded twisted pair had a metallic shielding around the twisted pair cabling, giving it increased immunity from electromagnetic interference. But it was more expensive. After all, we're wrapping the wires in a metallic coating that cost money. And with cost being one of the reasons, unshielded twisted pair really grew in popularity, and that is by far what we see the most of today. Even with unshielded twisted pair, we can still make ourselves somewhat immune from electromagnetic interference, EMI, just by, as we said earlier, creating a sufficient number of twists in the wiring. And this is by far the most common type of local area network media that we're going to find today. And on screen you see that we have different colors of wires inside of this unshielded twisted pair cable. There is actually a standard that says which color of wire needs to be connected to a specific pin on an RJ45 connector. The original standard was developed back in 1991. It was the TIA, the TIA/EIA 568 standard. By the way, TIA/EIA, which people commonly pronounce as TIA, that stands for Telecommunications Industry Association / Electronic Industries Alliance. That standard, which has now become known as TIA 568A, was updated in 2001, and that update is referred to as TIA 568B. And if you want to do an internet search to get the specifics on that, that can be a guide for you if you need to put an RJ45 connector on an unshielded twisted pair cable. The picture that we see on screen is from a particular category of unshielded twisted pair. This is a category 6A cable that we're looking at. Let's compare some of the different categories. First, we have category 3. Category 3 was often used in telephone, in PBX, in private branch exchange installations. And when Ethernet started to catch on with unshielded twisted pair, what you would be able to do is just use your existing telephone wiring to connect up to the network. You could be using 10 base T devices, which would give us 10 megabits per second. However, category 3 isn't sufficiently twisted for the kind of throughput that we would need for fast Ethernet or 100 base TX. Category 3 could go a little bit above 10 base T, however. If it was used in a token ring network, it could give you a speed of 16 megabits per second. But still, that's not enough for fast Ethernet, 100 megabits per second. That's where Category 5 came on the scene to help us out. With Category 5, we can run at 100 megabits per second for 100 base TX networks. And by the way, even though this isn't done very much, Category 5 cabling could even run at a speed of 155 megabits per second for ATM installations. ATM standing for asynchronous transfer mode. We don't see that much in local area networks, however. So generally, Category 5, that's going to be great for 100 base TX. However, nowadays, it's common to get a network interface card that runs at a speed of 1 gigabit per second, 1,000 bits per second. And Category 5E can give you speeds of 1 gigabit per second. And Category 6 can as well. Category 6 is a little bit better than Category 5E. For example, it may be made of 22 gauge or 23 gauge wire as opposed to Category 5E, which might be using 24 gauge wire. But be aware that some Cat 6 cable does use the same 24 gauge wire that's used by Cat 5E. But Category 6 cabling, as opposed to Category 5E cabling, Category 6 cabling has a thicker insulation. You might have a reduced amount of crosstalk if you go with Category 6 as opposed to Category 5E. And finally, down at the bottom of our table is Category 6A. That's what's pictured on screen. The A stands for augmented, and it can support twice as many frequencies as Category 6. And as a result, it's starting to be used in 10G base T, 10 gigabit per second networks. That's a speed of 10 billion bits per second. And we mentioned that this unshielded twisted pair cable is going to have an RJ45 connector on the end of it. Well, here's a picture of an RJ45 connector, and if you count, there are 8 pins. We had 8 wires, and there are 8 pins on this RJ45 connector. However, Ethernet, by default, is only going to use 4 of those pins. We're going to be using pins 1, 2, 3, and 6. There is a pair of pins, a pair of wires that we use to transmit data, and a pair of wires that we use to receive data. And if we get a regular Ethernet cable, like a Cat 6 or Cat 6A or Cat 5 or Cat 5E cable, and we try to interconnect a couple of traditional switches, we might run into an issue. Consider this topology. We've got a couple of Ethernet switches interconnected with a regular straight-through cable. And by straight-through cable, I simply mean this. I mean that pin 1 on the RJ45 connector on one end of the cable, it connects to pin 1 on the other RJ45 connector at the other end of the cable. And pin 2 goes to pin 2 and so on. The pins match up. Here's the challenge with that. Both switches, in this case, want to use the same pins, the same wires to transmit, and they want to use the same pins to receive. That's not going to work, is it? Because if I transmit from one switch over my transmit pair, it needs to show up on the other switch on the receive pair. Therefore, we could have issues with a straight-through cable. Instead, we might need to have a crossover cable. A crossover cable takes pins 1 and 2 and connects them to pins 3 and 6 at the far end. And pins 3 and 6, they connect to pins 1 and 2 at the far end. That way, the receive pair on one side of the cable, it gets connected to the transmit pair on the other side of the cable. Transmit goes to receive goes to transmit. We're able to interconnect our switches. This type of connector that we might see on a switch or we might see on a PC, it's called a media dependent interface, or an MDI. However, a feature showing up in a lot of Ethernet switches these days and widely supported on Cisco's newer Ethernet switches, their Catalyst switches, it's a feature called MDIX. Media Dependent Interface Crossover. If a switch port is configured for MDIX, it's going to be able to determine which pins need to be used to receive data and which pins need to be used to transmit data. That means that if one of the switches in the topology on screen had its port configured for MDIX, or if both switches did, we could use a straight-through cable. Even though it looks like we would be connecting the transmit pair on one switch to the transmit pair on another switch, we actually would not, because MDIX would notice that, and it would convert that transmit pair into a receive pair, and the receive pair would be converted into a transmit pair. It can dynamically shift the roles of those pins depending on what it detects it's receiving from the far end of the cable. Again, that feature is called MDIX. Fiber optic cabling is going to represent data not as electrical pulses, but as pulses of light. The absence or the presence of light is going to indicate if we're sending a binary 0 or a binary 1. And since we're using light to send data instead of electricity, this completely gets rid of the issue of electromagnetic interference, or EMI. We're immune from that by using fiber optic cabling. And fiber optic cabling tends to have a longer range. It can reach further distances than unshielded twisted pair. For example, let's say that we have a campus environment and we're trying to connect buildings around a college or a business campus. If the distance between the buildings exceeds 100 meters, that might be a great fit to use fiber optic cabling. When you go out to purchase fiber optic cabling and equipment, however, you should realize there are two primary types of fiber optic cabling. We have different types of connectors that we might see on a fiber optic cable. For example, there's an ST connector, or a straight tip connector, an SC connector, or a standard connector, an LC, a lucid connector, or an MTRJ, Media Termination Recommended Jack connector. The MTRJ is kind of unique in that within the single fairly small connector, we have two fiber optic strands. The connector you see pictured on screen is an SC, a standard connector, but we said there were two types of fiber optic cables. We have multi-mode fiber, abbreviated MMF, and we have single-mode fiber, abbreviated SMF. To help us start to understand the distinction between multi-mode fiber and single-mode fiber, consider what you may have seen at a restaurant. Let's say that you had a glass of water and you had a straw in your glass of water. You might have noticed a phenomenon something like this. When you insert a straw or a pencil or something into a glass of water, have you ever noticed that the straw or the pencil, those objects don't seem to line up above the water line and below the water line? What's happening is something called refraction. Specifically, air and water have a different index of refraction, a different refractive index, meaning that light travels at a slightly different speed in water and in air, causing the light to bend. That's what's happening with a fiber optic cable. If we were to zoom in on a strand of fiber optic cabling, it would look something like this. And by the way, we have two strands typically. when we're connecting a piece of equipment. One strand is for transmission and one strand is for reception. Here on screen though, we're just zooming in on a single strand of fiber optic cabling, and you'll notice that it's not a single piece of glass. You'll notice that we have an inner core, and outside of the core we're surrounded by an outer cladding. We have a core, let's label these. We've got the core, and we've got the cladding. And the index of refraction is so different between the core and the cladding, just like the glass of water would bend the light a little bit. The indices of refraction are so different between these different pieces of glass that the light literally bends back on itself. It cannot escape the core. It's going to work something like this. We have a beam of light, like a laser or an LED coming in. It hits the edge of the core, that barrier between the core and the cladding, and again the index of refraction is so different that it's going to bounce off, and it bounces off the other side, back and forth, back and forth. It bounces its way down the core of the fiber optic cable. And with multimode fiber, the core has a diameter that's large enough to allow light to enter the core at different angles. I showed the light entering at one angle. What if we entered at a steeper angle? Like this. If I entered at a steeper angle, there's going to be more bouncing involved, isn't there? Back and forth, back and forth, back and forth. Do you see what's happening? It's taking us longer to get out of the core because we're bouncing back and forth more frequently. Over a long distance, such as greater than 2 kilometers, we could have an issue with this. If one bit comes in at a steep angle, like the green line on screen, and the next bit comes in at a less steep angle, like the red line on screen, it's possible that the bits would get out of order. The first bit came in first, but it bounced back and forth, back and forth, back and forth much more than the next bit did. It could actually fall behind. The name for this is called multi-mode delay distortion. A mode is a path over which our light is going to propagate. Light is going to travel over a particular path. That's a mode. I've drawn 2 modes on screen, but we could have lots of modes with this particular fiber optic cable because the diameter is large enough to support multiple modes to be transmitted. It's less expensive to manufacture a multi-mode cable. The way it's manufactured is there are different levels of dopants put in the core and the cladding to give those 2 different types of glass a different index of refraction. But if we have higher manufacturing tolerances and we can have a smaller diameter, if the core is smaller, it could be so small that we would only have room for one mode. In that case, our mode of propagation could only go down the middle of the core. The diameter is not large enough to allow light to enter at another angle. That's not going to work. A larger angle of incidence, as it's called, is not going to be supported. Because the diameter is so small, we only have one mode, only one path that the light can take. That's called single mode. And because single mode eliminates the issue of multi-mode delay distortion, because we don't have multi-modes, this means that we can achieve much greater distances, maybe 40 kilometers as an example, with single mode fiber as opposed to multi-mode fiber. But to sum up, fiber optics, it's going to represent data as the presence or the absence of light. Therefore, it is immune from electromagnetic interference. It's often used when the distance requirement for a connection is greater than that supported by unshielded twisted pair cabling. It supports high data rates, and we have 2 types. Multi-mode, which is less expensive than single mode. And the reason multi-mode is less expensive is it has a larger diameter for the core, which could allow multiple modes, multiple paths of light to go into the core, which could result in multi-mode delay distortion. That issue is eliminated with single mode fiber.